Thanks, Will. And our fourth speaker, even though she comes from Minnesota, but actually right now, she will be giving her talk all the way from Italy. So hopefully the connection is fine. The background looks beautiful. I'm not sure if that's where she is. Most likely she's somewhere with a Wi-Fi. So let me introduce Professor Laura Gagliardi, who was born in Italy and giving her talk from Italy. So she obtained her PhD in theoretical chemistry from the University of Bologna, which I believe where she is right now. She then spent 2 years in Cambridge, UK as a postdoc and began an independent career in Palermo, Italy as an assistant professor. Then she moved as an associate professor to the University of Geneva. And after that, University of Minnesota were smart enough to recruit Laura, and now she is a McKnight Presidential Endowed Chair, the Director of Chemical Theory Center, and my boss and the Director of the Inorganometallic Catalyst Design Center. She will be our neighbor soon because in September, Laura will join the chemistry faculty at the University of Chicago, where she will also be the director of the Chicago Center for Theoretical Chemistry. So Laura needs no introduction, but she is a computational quantum chemist who is internationally known for her contribution to the development of electronic structure methods and their use for understanding energy relevant chemical systems and materials. She received many recognitions from the chemistry community, too many to list. I decided to only name a couple. Recently, the Peter Debye Award in Physical Chemistry from the American Chemical Society, the Humboldt Research Award, and recently was elected to the American Academy of Arts and Sciences. Please help me welcome Professor Gagliardi.
Thank you very much, Omar. Can you hear me?
Yes, we can. Okay.
So, well, it's an honor to be participating to this meeting. I found the previous talks very interesting and very inspirational. And so now we switch gear a little bit and we'll talk about some more fundamental aspects. And in particular, I will talk about modeling gas separations in metal organic frameworks. And I will give a couple of examples and hopefully, besides the achievements of these examples, I think I'd like to hope that the methodologies that we propose may help the community also to model other problems related to porous materials and separations in these materials. So I will tell you to go next. So go next, please. So from a computational point of view, and again, we are going very fundamental, but we have to, when we study these materials, we have to model them at different length and time scales. So you see on the left, you have a molecular system. And of course, we have to understand these systems really at the molecular level, and this is where my background comes from. And then in the middle, we have maybe the nanoscale, which is probably a MOF. And then on the right, the mesoscale, which is even more complex in terms of extensions and time scales. And sometimes we have to go there. So bridging these scales is a big challenge computationally. Today, I will mainly talk about the atomic, molecular, and nanoscale. Next, please. Can you hear me? Okay, so I also have this slide. This is a slide taken from some previous work of the group of Randy Snur, and also Omar, I think, is a co-author of this paper. This slide summarizes why theorists love MOFs. And we have heard before about the rigidity of these systems. So ideally, what a theorist could do is take some existing MOFs, the ones on the left, and then just classify the building blocks, the inorganic component, organic component, and then combine them. In this particular paper, the criteria were just geometric, and in such a way predict hypothetical structures. So in this original study, Randy and co-workers predicted about 100,000 hypothetical structures just by geometric consideration. Of course, then one has to see which of these are suitable for a given application. But this is the rigidity of these structures is certainly one of the reasons why theorists love MOFs. Next. So I'm going to tell you two stories today. One is about CO2 separations and CO2 capture in a metal organic framework. And I want to show you what theory can do. And the other is about the oxygen nitrogen separation. So probably I don't have to explain to this community what are the current separations ongoing in industry for CO2 capture. So either post-combustion, pre-combustion, or an oxy-fuel combustion. Next. And I want to tell you about a story. This is a collaboration with Jeff Long. So Jeff has been working on these metal organic frameworks, metal MOF 74, where the metal can be any first row transition metals or also second row. Next. And so here, what is important about these materials is the local environment of the metal. So the metal is coordinately unsaturated because of the way in which it has been, the material has been synthesized. And so this site can be a good binding site for gas like gases. Next. So here you see in this animation, you see a molecule of CO2 getting close to the metal. And so you have this metal with 5 oxygen atoms, and then the linker is this benzene decarboxylate. Next. So this is a picture taken from a paper by Jeff a few years ago. And so if one wants to have a good absorption of CO2, the goal is to be achieved not just when CO2 is by itself, but also in a mixture. So the materials on the right on these plots, and these are MOF-based materials, are particularly good because the CO2 absorption is very high also in the presence of other components. Next. So now the theory part is the following. I mean, what type of questions can we try to address? So if we think about this topology of this material, which metal is the best for CO2 capture? And we would also like try to understand why this is the case, and then based on this understanding, predicting new materials for a given application. Next. So usually when theorists perform this simulation, this modeling, what they have to do is to perform a classical simulation, for example, a Monte Carlo simulation, because we have to capture the collective behavior and the statistical behavior of these materials. And so to do so, for example, if we want to study the absorption of CO2 in one of these MOFs, we have to be able to describe the gas-gas interaction, for example, CO2-CO2. And there are very well-established force fields. For example, the one developed by my colleague Ilya Sipman, the Trappe force field. And then for the host-gas interaction, there are various force fields in the literature. These are usually Lennard-Jones, so you have a 12 R to the minus 12, R to the minus 6 terms, and eventually some charges. But these force fields have not been developed for MOF specifically. They've been parametrized for other systems, for example, biological systems. Next. So here you see the performance of these existing force fields to describe the absorption of CO2 in magnesium MOF 74. And the field symbols correspond to 2 experimental curves, while the empty ones correspond to the force field. And the performance of this force field is not so exciting. I like to cite my colleague Darren Smith, who says MOFs are not as universal as these force fields. So there is a conceptual problem there. So let's see how can we address that. Next. So what one can do is to parametrize these force fields, not from experimental data, because sometimes these experimental data are not available. There are not enough of them, but directly from quantum chemical calculations. And so here you see in this picture on the right, the red curve is a quantum chemical curve that describes the interaction between magnesium and CO2. And then one can divide it up into the various components of these interactions, for example, electrostatic, dispersion, and so on. And the beauty of this approach is that one can use it also when experimental data are not available, if the materials have not studied enough. Next. So when we compute these interactions, we, as I told you, we use quantum chemical approaches, and we can use a variety depending on the type, the system that we want to model. So if, for example, we want to compute these interactions for the entire periodic system, so we mainly use density functional theory. On the other hand, we can also construct some cluster models of various sizes, and for these cases, we can use wave function based methods, which are probably more accurate to describe the local structure, but they are more expensive. But we try to use all these hierarchies and see when we have an agreement in the description. Next. So here you see this magnesium CO2 interaction. So one starts from this quantum chemical calculation. You see the curves on the left. And then we try to, so we describe this interaction as a sum of a repulsion, dispersion, polarization, and electrostatic. And then we try to go, moving from the left to the right, to a slightly simplified expression, which we will finally fit into a potential. And you see this interaction, final interaction, interaction energy expression, where there is this Lennard-Jones term, 1 over r to the 6th, and also an exponential term, which is a banking down kind of potential. So this is just a little bit about the methodology that we use. Okay, next. And so here you see these are some predictions from these first principle force fields or ab initio force fields. And here we have the panel on the left. We have with these potentials that we generated, we have the area coefficient for pure CO2 as a function of temperature. And you see we have the experiment, or the blue circles, the green triangles. So these are the conventional force fields, so not very satisfactory. And then we have our red results with this fully ab initio derived force fields. And so this is quite exciting. We also try to do it for N2, not just CO2, to see if we were equally accurate. And also in this case, the results are quite good. And these simulations were done in collaboration with Baron Smith when he was in Berkeley. Next, please. So we also, here we have the adsorption isotherm. So we have the loading of the gas as a function of the pressure. And you see in this case, our force field, which is the red one, agrees with experiment quite well at low pressure. When we go to high pressure regimes, the agreement is not so great, because of course the material has becomes more complicated. For example, there is a CO2 clogging, or maybe there is some residual solvent that we don't have when we compute the pure quantum chemical interaction. But you can see that this approach is significantly superior to traditional force fields. Okay, can you go next? So what we did as a follow-up of this study was to look not just at magnesium, but also at other metals. And again, here, the idea is to try to reproduce the experimental data, because they are available. This is a way for us to validate our approach and build confidence in that, and then eventually use it to predict something not yet measured. And you see in these curves, we were able to predict good agreement with experiment also at a high pressure. But to do so in the simulation, we had to include further effects. For example, they were to factorize in the pore blockage, because this occurs in the real material, and also the presence of some residual solvent solvent molecules. Okay, next. Thank you. So to summarize this part of my talk, now I have some, you can go ahead, so just show me one at a time. So yeah, you can show all of them if you want in one slide, okay. So basically we were able to parametrize these force fields from quantum chemical calculation. And again, this is a procedure that has become more and more popular when not enough experimental data are available. And of course, this doesn't mean, because sometimes people say we want to be truly accurate because we are first principle. No, if there are experimental data, of course, the accuracy of the force field would be superior, but sometimes this is not the case. And also, one can vary the composition of the material. So for example, vary the components of the linker or the connectors and explore new materials. And ideally, these force fields are significantly transferable from one system to another, that they can be used. So in the future, our plan is to look at different adsorbates and also explore more the transferability of these force fields. Okay, thank you. Next. So now I want to give you an example of another separation. And this is O2 N2 separation. And of course, again, I don't have to explain to this audience why this is important, but O2 has various uses in industry, chemical manufacturing, combustion, medicine, and N2 also is very important, especially as feedstock in ammonia synthesis. So the current separation technologies are based mainly on cryogenic distillation. And of course, one area of research is if one can envision a membrane-based methods. And so MOFs in this respect are very promising. Okay, next. So in particular, what is interesting are systems in which one attaches a metal catecholates to the linker of the MOF. So here, for example, you see some zinc-based MOFs with vanadium catecholates. And these catecolate functionalized MOFs are very appealing because the catecolate can be incorporated into the MOF post-synthetically, and one can generate, again, these low coordinate open metal sites. And these are very accessible to the guests, or oxygen or N2, for example. And there is this strong interaction between the under-coordinated metal catecolate and the sorbates. Next. So we started this study at a very fundamental level. So we just looked at these metal catecholates. And so on the left, you see M is the metal, and we explored mainly first row transition metals in formal oxidation state of +2 to have neutrality in the system. And here you see O2, which is bound to this metal catecholates. And we compute this binding energy as the difference between the energy of the super system minus the two subsystems. Next. And so if we just look at these simple cluster models with a catecholate, here we see the binding energy of O2 and N2, so to try to understand this separation. And here you see the behavior of different transition metals. So ideally, if one wants to find a metal that is good for this separation, one would like to have a big difference between N2 and O2 in terms of this energy, but at the same time, it shouldn't be too large because we want to bind the oxygen or N2 and then to release them. So this is the performance of different metals that we were able to compute for just the bare catecholate. Next. So what we decided to do afterwards was to not just look at, I mean, the bare catecholate is a very approximate model for the real systems. So we decided to screen a big data set of MOFs, and this was done in a multi-stage process. So we looked at just pristine MOFs from the core MOF database. I will tell you more about that. And then we just explore structural criteria. And then we did this grand canonical simulation of these binary mixtures for O2 and 2 to see which ones are promising among these MOFs for the separation. And then for those that are promising, we decided to metallate them, so create this catecolate. And for the promising one, we performed DFT, so first principle calculations, and computed the binding energies. Next. So here we started from this core MOF database, which is, so these data come from experiment, but they have been readjusted computationally so that one has, for example, no solvent molecules attached or so on. And this is about 5,000 structures. So these are 3D MOFs, solvent-free structure, and the pore aperture diameter is larger than the hydrogen molecule kinetic diameter. So we started from this data set. Next. And then we decided, I mean, the idea here is we want to metallate the linker. So we need to have a 6-member ring containing carbon or nitrogen, but also there have to be 2 consecutive carbons with hydrogens, because these is where the methylation occurs. The catecolate is formed. So the structure on the left, for example, or similar structures are discarded, while those on the right are accepted in the follow-up step. Next. And then, so in such a way, we basically go from 5,000 to about 3,000 MOFs. Next. And then there is another consideration that one is to make, and this is about the pore characteristics. So we need cavity diameters such that it's possible to have the methylation, so they have to be larger than 8 Armstrong, but also the pore limiting diameter has to be such that oxygen diffusion is possible. So we impose these 2 extra criteria. And also, we have to perform some Monte Carlo simulation. So we need metal types such that they have, so that the ionization potential and the electron affinity of the metal is known, so that we can generate reliable charges for the simulation. And also we decided to exclude lanthanides and actinides. Finally, we wanted to limit the number of atoms per unit cell to be able to perform these DFT calculations. So we just consider systems with less than 300 atoms per unit cell. Next, please. So this means with all these restrictions, we restricted our number of candidates to about 260. Okay, next. And then on these 260 MOFs, we performed the grand canonical Monte Carlo simulations to explore the O2 versus N2 selectivity. And here there are some details of these calculations. So what we compute is this selectivity expressed by the formula on the right that tells us the number of molecules of oxygen and 2 per mole, and the fraction of these 2 components. And basically we decided to include in the follow-up study only the systems which have an S equal or greater than 1. Next, please. So this basically reduces our set to about 210 pristine MOF candidates. Okay, next. So now at this point, we have these pristine MOFs. We want to metallate them. And so we have these 6-member rings with or carbon and nitrogen. And we have to replace 2 hydrogen atoms with 2 oxygen, and then add a metal atom. So we basically go from these bare rings to this metal catecolate structure in the bottom right. And then we bind O2 and N2, and we calculate the binding energy. Next, please. So of course, there is another technical problem, which is we have multiple 6-member rings, and also one ring may have multiple potential methylation sites. So if you go next, we see the possible, so this is one possibility. Next, please. You have 2 and also the other one. So these are different methylation sites. So if we did that, okay, there are 5 minutes remaining in this session, but I must say that I started much later than so Omar, how much time do I have?
You have,
hello?
You have 6-7 minutes, Laura.
Okay, I will make it. Yes, for sure. So we would have all these huge data set, if you think. So next, what do we do next? We considered only, I mean, we included some symmetry consideration, and so basically considered only one methylation site. And next, please. And so at the end of the day, with all these further constraint that we imposed, we end up with about 20 different MOFs. And we will have 20 unique methylated structures, 2 gas types, 3 different configurations. So we have to perform about 100 DFT calculations. Okay, next, please. So these are, at the end of the day, based on all these considerations, these are the top candidates for the DFT calculations. So these are 3 MOFs topologies. EduVOO is a zinc base, then we have MOF5, and then we have UIO with 2 transition metals, zirconium and cerium, because these were the ones that gave the best potential overall. Okay, next, please. So here we go back. Now these are back just cluster calculation without the MOF, just the metal catecolate. And we are considering all these different transition metals. And again, here we see the binding for O2 and N2. And we want to have these 2 bars different, but we don't want to have overbinding, because then we will not be able to remove oxygen. Next, please. So by looking at the relative energetics, and also we want to have basically, I mean, ideally we would like to have 20 to 40 kilojoules for N2 and, sorry, for O2 and about 0 for N2. So these ones are highlighted in yellow are the top candidates. So as a methylation center, so magnesium, or we have cobalt, nickel, zinc, and cadmium. Okay, next. And so here there is this considerations that I already told you about, so we can move on to the next one. And so here these are the results from the periodic simulations. So we include the entire environment. So here we have those metals in the metal catecolate and the MOFs that are our favorite candidate. And you can go next now. So we just see that the MOF structure has a limited effect. The metal in the metal catecolate seems to be more important. Okay, next. So if we look at the strength of O2 absorption, we see this trend. So magnesium catecolate is greater than cobalt catecolate, greater than nickel, which is similar to zinc, and this is greater than cadmium. And then we have also the trend of the N2 absorptions. So at the end of the day, remember, we don't want too much binding. So you can go next. And also this is the ratio in terms of separation and selectivity between O2 and N2. And this is estimated only for low pressure absorption. So next, please. Based on all these considerations, the cadmium catalyst system have the lowest absolute O2 absorption energy, and also the low absolute N2 absorption energy. And if we look among the cadmium system, the lowest absolute O2 binding energy is in this EduVOO cadmium catecolate system. Of course, there is a problem that the regeneration at low pressure may be difficult, but at higher pressure, partial structure regeneration is possible. Next, please. So this is the conclusion. Basically, we think that these metal catecolate functionalized MOFs have the potential to produce high purity oxygen. And in order to achieve this conclusion, we performed this multi-stage computational screening. And it seems that the structure effect of the MOF on O2 and N2 binding strength is minor. On the other hand, the nature of the metal in the metal catacolate seems to play a major role. And in particular, we identified this candidate with cadmium. And of course, if one has to think about making the real material, there may be some regeneration issues that could be overcome by these suggestions. Next, please. So this is a sort of conclusion talk, not just about this particular conclusion slide, not just about this particular example, but in general about this area of research. So if we want to study these separations, absorptions in metal organic frameworks, but also COFs, one needs certainly a multiscalar approach. And we need, if we look ahead, to find better ways to model defects, also nuclear electronic interactions. And sometimes you have transition metals, so strong correlation becomes important. Also, I've given you an example in which everything has been done manually, really by humans, but what becomes more popular, and we are working in that direction in collaboration with Omar, for example, is to use this quantum chemistry calculation results and experimental data to develop artificial intelligence, machine learning techniques, so that we don't have to perform all these calculations or all the experiments, but the machine can guide us. And also, it's important to remember from a computational point of view that the computational resources, the computers are evolving fast. We have exascale computers, we have quantum computers. So one of our goals is also to develop better algorithms for these platforms. Next. So with that, I want to conclude. So this is a picture of my group before COVID. Now we have a different one, but we look a little sad, so I decided to leave the one outdoor. And I've highlighted the names of the people who have collaborated on this project, and also the experimental collaborators, Omar Farah is our experimental collaborator, and the theorists, so Randy Snur, Chris Kramer, and Ilya Sipman, and DOE for funding. And then if you can go to the next one, just to thank all of you for your attention, and if you have questions, I'm happy to take them. Thank you.
Thank you, Laura. So now we could open the questions for anyone who has from the audience live. If you have a question, unmute yourself and ask your question. Okay, I see Todd there.
Hi, Laura. Thank you. Nice talk. I'm curious, on one of the last slides there, you sort of laid out several of the places to improve things. And it seems to me that the defects probably are a place where you're going to have sort of the biggest contribution to the error bars on these types of calculations. I'm curious if you could share your thoughts on, you know, the scale of the error bars and what you think is going to dominate that.
So, of course, in these simulations that I presented today, we didn't include defects because we treated, at least at the quantum chemical level, when we do this quantum chemical, we treated these materials as perfect crystals, and this is a very strong approximation. So what we have found, but again, it's trial and error, is then you factorize these defects in the classical simulation. So, for example, we say, I don't know, we have a 30% of pore clogging, or 30% of remaining solvent molecules, which probably are absolutely unrealistic values, but they were the values that allowed us to get agreement with experiment. So I think at the moment it's still a trial and error. I don't think there is a straightforward way to include these defects, also because sometimes we don't know what they are, and they also change under different conditions. So one thing is when you maybe synthesize the material, one thing is when the material is under some process. So it's certainly a big challenge for our community, but that's, I think, why things are so exciting, so fun. Okay? Can you hear me?
Yes. Thank you, Laura, for not throwing the experimentalist under the bus. So thank you for that.
No.
I said thank you for not throwing us.
Experimentalist. It's a very
we are having some technical.
It's just a very difficult problem, and we are trying to address in a very simple. Okay.
So to take one more questions from the audience before we move on to the next speaker. So Laura, one of the questions says, what is the best metal cluster for CO2 adsorption so far?
I mean, I think that at least in that topology of a MOF 74, it seems it's magnesium, because probably the binding is strong, but not too strong. So this is purely from a chemical point of view. Of course, there is the engineering point of view, which is another one which I haven't addressed. But I would say the interaction that we were able to describe as magnesium is in the right ballpark. Some metals are binding too strongly, others not enough, and so you want to reach this idea zone. And I have the metal, but experimentally, some of these MOFs, I mean, they were able to make better crystals than others. So if you can only make a powder, I mean, it becomes probably less interesting, less exciting for applications.
With that, Laura, the questions will stay around. There is a couple more questions, if you don't mind answering.
Yeah, I will. Shall I answer them by text?
Yes, please.
Okay.
Please join me once again virtually thanking Professor Gagliardi for being with us today. Thank you, Laura.